This video was produced for the use of all students enrolled in the EPO 322 Diesel Engineering 2 simulation course held at Cal Maritime. This is the first of a two-part video lecture on marine vessel electrical distribution systems. All PowerPoint presentations for all 6 lessons are available on Moodle. The opening frame of each of these slide presentations will give you the reading that assignments for that lesson. It also will list elective background reading material, if appropriate, that is to help for those that want to dig deeper into the material that we are covering. And those will also be listed. For this presentation, no reading has been assigned related to the subject matter. The following reference material is available if the student wishes to dig deeper into the subject of electrical distribution and automation. And again, you can, as this is available in your syllabus, or you can download the presentation itself online. The learning objectives is describe the major components and design of a shipboard electrical distribution system, give the student an awareness of how vessel power is distributed, give an overview of the new cold ironing regulations that are applicable in a California berth, and an overview of vessel automation required for unmanned service certification. At the end of this lecture, the student should have a better understanding of the importance of an electrical distribution system to the safe operation of a vessel, how power is distributed within the vessel, how the emergency switchboard provides backup power to critical electrical circuits, the importance of modern instrumentation and a distributed control system to the control and monitoring of a modern vessel operating under UMS. Also, how the new regulations affect the operation of a vessel when it is berthed in California. This is a listing of worldwide what are the standard system voltages. Also, generation and power. There is a small voltage drop between the generators and the main switchboards, and that's the difference between these two. So typically for your large equipment, most ships are 440 volt 3-phase power. You will also see listed here with higher voltages and kVs, 1000 volts, 2.3 to 13.8 kilovolts. Within the Americas now, we are seeing 6.6 kilovolts and 11 kilovolts on ships. These high voltages are on vessels that use that use electric propulsion, and you need that high voltage to keep the amperage going to the motors within reason. Also for lighting, it can be 115 or 220 volts, usually single phase. The electrical power is generally routed through the ship's electrical service system in an arrangement known as a radial system. What this means is that typically the power from a switchboard to the actual piece of equipment, there is only one source. And this is done for safety reasons. If it was to come from multiple sources, you have to make sure, and before working on a piece of equipment, that you cut off power to every source. So generally, from any electrical consumer, there is only one continuous path back to the source of electric power. Some vital equipment can be energized from an alternate source in an emergency, but particularly only one protective device or disconnect is necessary to isolate a piece of equipment or section. And again, this is for safety. In the case of the simulator, the number 2 ventilation can be supplied, and that is, both your exhaust and supply blowers can be supplied from either the emergency or the main switchboard. That's the only piece of equipment that breaks this rule. And if you're operating on this vessel, it would be important for you to know that and be conscious of that in case of emergency has occurred, to protect yourself from being shocked. In other words, in this case, you would have to go to both the main switchboard and the emergency switchboard, open both of those breakers to prevent electrical shock if you were working on that system. Typical large vessel installation is 450 volt, 3-phase, supplying 440 power to consumers, and 115 volts on American vessels to lighting. European is 220 volt, single phase is the typical circuit. The power panels themselves may be single phase, or there may be 3-phase power coming into that power panel. My experience has been the power panels themselves are typically 3-phase. There is a 4-wire system, which is, you would have, typical to any 3-phase, you would have 1 wire, in other words, 3 wires for each of the hot power leads coming in, and then you may have a neutral. A neutral is typically used on a merchant vessel with a delta type distribution system. This is kind of beyond our scope within this to go over this in detail, but just realize in your home that you have supplied 2 hots and a neutral. If you go between a hot and a hot, you get 220 volts. If you go between a hot and a neutral, you will get about 120 or 110 volts. Let's put it that way. So this is your house is a wide distributed system. There are some vessels like this, but it is fairly unusual. Shipboard main low voltage systems are normally insulated from earth, which means that the high voltage distribution systems usually have their neutral points earth through a resistor or earthing transformer to the ship's hull. Again, this gets into 3-phase electrical theory, which is more than what we really want to talk about in here. But what I want you to understand is that on our generators, they are 3-phase. They are connected Y, and the center of the Y in a shore-based generator would be insulated to ground. On a ship, it is typically removed from the ground, which would be the hull. That means that if one of the hot phases goes to ground or touches the hull, there is no return path back to the generator, or a very limited return path back to the generator. This is done for safety reasons. If you are operating a vessel and that vessel is going into port, and your steering gear, the motor driving the hydraulics for the steering gear, develops an earth ground, that will bring up a indicator that you have a ground, either through lights or in modern ships it actually comes up on the alarm system, on the automated alarm system, that is, a ground has occurred. But there will be very, very limited current flow and the motor will still operate. Shoreside, since there is a return path back to the generator, if a ground develops on a piece of equipment, then the breaker, the high current will flow and the breaker will immediately open. Now, this is the case in your house. If you would short a circuit in your house, the breaker will immediately trip. You go to your breaker box, you open it up, you can see the trip breaker. It's very easy to find the problem. But for safety reasons on a ship, we don't necessarily want a circuit to trip we want that equipment to continue to run until the operator has time to switch over to the redundant system and turn off the system that has been grounded. This is called a one-line circuit diagram. It's very typical to find in the distribution, let's say behind the main switchboard or up in the emergency board. And it gives a simplistic outline of the distribution system on a ship. Now, this is for the training vessel. And you can see that it has 3 900 kW diesel generators. It tells you that where it's going to a vital motor control center, non-vital motor control centers. You have a transformer that's reducing the voltage from 450 volts down to 120 volts for your lighting system. And then on this side, we're going. We have a separate lighting bus on this. And in the case of the Bear, you actually have on the left-hand side of the main switchboard, you have that 120 volt in its own little switchboard, and you have individual breakers attached to that. The one thing I want you to note is that there are 3 separate generators here. In this case up here, this would only be used in an emergency, but if you had a major emergency, you would have to, where a part of the board, say, was destroyed. So let's say this part of the board, there was an electrical fire and has been destroyed. You would have to shut down all power to the ship, and then including the emergency generator. Everything would have to be dead. You can get in behind, and then mechanically, and I mean you'd go in there with a socket wrench, and you can unbolt part of the bus to separate this board. And then you have these 2 generators that you could bring online to power up this side. Though you do have anything on here, like here you have a vital motor control center. Hopefully this would be port and starboard, or you would lose, say, your redundant units, but hopefully you would be able to power up the vessel. The symbology here, these are circuit breakers. And the symbology on this is a fuse. And then down here we have our emergency bus. And we're going to go over this more later on. But what I want you to notice is there are 2 circuit breakers connecting the main switchboard to the emergency switchboard. Okay? And these are typically called bus ties. Now, you don't typically have 2 circuit breakers in the same line. That's unusual. And this is not done so much for the protection of the circuit, but for the control of the circuit. This particular tieback breaker is down in the engine room, and it's manually actuated. This circuit breaker is up in the emergency diesel generator, and it is tied into the control so that both the electronics can control both this circuit breaker and the disconnect circuit breaker on the emergency diesel generator. You also have a battery charger, and you've got your backup batteries on a 24-volt DC bus that controls lots of your vital equipment on board the vessel. And again, we will go through that as part of this presentation. So all vessels are provided with an emergency electrical power source which will supply power in the event of a major power failure. The emergency power can be supplied by engine-powered generators, batteries, and the batteries are there in case the worst case scenario that your emergency diesel generator doesn't start. At least you have batteries, which typically is very reliable to give you some power for your emergency. But the batteries are going to be very limited, and they are going to drain and lose their charge over time. They're fairly short-lived. Your emergency diesel generator usually has enough diesel fuel in its tank to at least be able to supply power for a minimum of 24 hours. The emergency switchboard provides power to emergency lighting, firefighting equipment, alarms, communication, navigation equipment, and any other service necessary to maintain safety and permit safe evacuation of the vessel. So there's been some fairly high profile one, of course, and we will talk about a couple of those incidents involving loss of power on a vessel. And I want you to think about this, that in an emergency, if you've lost your main generators, anything that is vital to your survival or the ability to call for help has to be, there has to be a secondary source of power to do this. So your emergency generator, emergency lighting, you have to be able to move around the vessel in an emergency and not be in the dark. And you may not think about that, but I will bring up that you always want to carry a flashlight on a vessel. I personally have been caught in the hold where we lost all power, and then I dropped my flashlight and broke it, and I'm trying to find my way out of a totally dark space. So that's what that is there for, is to prevent that type of an accident, so that you have enough lighting in an emergency to at least attain egress and be able to leave. Of course, for the most part, firefighting equipment. If you have a fire and it's in the engine room, it's not unusual to lose your main generators. You need to have the ability to run your firefighting equipment. Alarms. You want to, and those two, the alarms typically also may come off of the battery supply. So again, even if the emergency diesel generator doesn't start, you at least have alarms telling you vital information about that emergency. You have to be able to communicate with the Coast Guard and with the company itself to be able to communicate your distress. Navigation equipment is under the emergency lighting. And again, any other service to maintain safety and permit safe evacuation of the vessel. So even anything to do with the lowering of the boats. I've even had vessels that I've been on that in an emergency, let's say a flooding emergency, you can hit one switch and all of your skin valves on the vessel automatically close. Any of those types of systems. So the emergency switchboard provides for control, protection, and distribution of power required for the proper operation of the emergency electrical plant. It includes the necessary automatic transfer equipment to maintain power for the ship emergency loads for either the ship service switchboard or the 300. This is in the case, by the way, of our school ship. That the emergency diesel generator is 300 kW. Now, our main generators are 900 kW. And there are differences in the way that they are set up. Our main generators are able to parallel with each other. They have governor control that allows for droop. And droop is necessary to allow, and this is the speed governor, to allow for parallel operation. But the emergency diesel generator is asynchronous. In other words, its governor is set up to maintain always a certain RPM, and it cannot be, in the case of the majority of American vessels, the emergency diesel generator cannot be placed in parallel with one of the main generators. And that is a definite limitation. We'll talk about this towards the end of the presentation, but that is somewhat changing in today's world with cold ironing, where you're having to shut down the engine room and shut down all internal your auxiliary ship service diesel generators while you're in port. Those vessels, you're going to see new regulations in the works that will allow them to automatically parallel. But any of the older ships, this was not available. So your 24-volt DC distribution panel, remember what's going on this is your emergency battery backup, right? So one of the things on this, internal communications, that has to be maintained no matter if your emergency diesel generator doesn't start. And I've had, at least personally, 2 major emergencies where the emergency diesel generator, for various reasons, didn't start. You've got to have internal communications. The ship surface diesel generator, in many cases now, they're not self-exciting. They need power from the main board to be able to raise voltage. So that would have to come off of this 24-volt DC distribution panel to make sure that if you've lost power, that you can start a diesel generator and that generator will bring up voltage. Emergency general alarm panel and an engine room 24-volt distribution panel, which in many modern ships now, that's going to be supplying all your automation loads. So the emergency switchboards includes a 120-volt distribution that provides power to other emergency loads like your gyro, the wheelhouse, bridge console, IC battery charger. This is a picture of our emergency diesel generator room. There's a couple important points that I want to bring up. One of them, it is outside. You can access it from the exterior of the hull. In other words, if there was a fire inside on the vessel and the passageways are filled with smoke, you can still access this room. It is in a very protected area. It is up high. It is behind the house to protect it from wave action. In case that there is a vessel flooding, even with the majority of the vessel flooded, this room would still be operational. It is outside of the engine room and well away from the engine room, so that if you have an engine room fire, this emergency diesel generator will not be affected. Another thing is, in the case of this, it is the space in case it catches on fire is CO2 protected. You do have this nice watertight door, but beside it you have a louver that is to allow airflow to the radiator. Unfortunately, don't think because it has a watertight door that this space is watertight. If a wave was to hit those louvers, it'll punch through them and it can flood the space. But that's part of its design, unfortunately. Now, one other thing to bring up is that an emergency diesel generator has to be standalone. It has to have everything in that space it needs to operate it, and you want as simple as possible. So it is going to have engine-driven pumps. It will typically be air-cooled with a radiator. There is, in this case too, you have the emergency generator day tank to supply you with a minimum of 24 hours of fuel, and you have a hydraulic start system on this vessel, which is very, very good method. It gives you the highest cranking speeds. Now, the other thing, though, anytime, let's say you are directed by the chief engineer to start this generator up, one of the major things that you always want to do is when you start this diesel generator or prior to starting it, of course, make sure that you have lube oil in the sump, check your radiator for cooling water, check your fuel supply. Another one that I will bring up just briefly is you have on here a trip, and this trip's an air damper. Make sure prior to trying to start it that is not in the trip position. Unfortunately, I've been on a vessel where I've had an engineer that shut down the emergency diesel generator by tripping that and then not resetting it. So in an actual emergency, the generator could not start because it could not inhale, could not breathe. So always make sure you don't want to drain your start system in an emergency. Then this is the board. You have your voltage regulation down here. You have your watt meters, watts, volts, hertz for frequency, and you have your controls for the generator itself. This guy down here, this is for the feedback feature. And again, there is a key that goes in that to disable it, because when you disable this, you are disabling a vital safety interlock. And again, the Europeans actually disagree with Americans. They do not have this feature. So our next subject is the automatic bus transfer. During normal operating condition, the emergency switchboard bus is energized from the ship's service switchboard through two emergency bus tie circuit breakers, one on the main switchboard, one on the emergency switchboard. This panel also controls the automatic bus transfer switch necessary to accomplish an automatic emergency sequence which would transfer the emergency bus supply upon a loss of power of the ship's switchboard. This system also provides for automatic retransfer of the emergency bus supply to the ship's service switchboard upon reestablishment of normal voltage on the ship's service. An electrical interlock between the emergency generator disconnect circuit breaker and the emergency bus tie circuit breaker is provided. And this interlock prevents the inadvertent paralleling of the emergency generator and the ship's service diesel generators. Okay, so here's our one-line diagram again. This is my main switchboard. This is my emergency switchboard, emergency generator bus tie, disconnect circuit breaker, emergency diesel generator disconnect circuit breaker, the emergency bus tie, and the bus tie on the main switchboard. So if we're out at sea, the ship's operational, one or two of these generators is going to be supplying the main bus. For whatever reason, we lose those generators and we have a blackout condition. The system, the automatic bus transfer system, senses voltage right here just before the emergency bus tie. If that voltage goes to zero, it knows that there is a blackout condition. The first thing that it's going to do is it's going to open the emergency bus tie circuit breaker. So this breaker opens so that these two switchboards are now separate and are not electrically interconnected. Then it will start the diesel generator up, and it will close the emergency generator disconnect to power up the emergency board and all the supplies on that. So the main switchboard will stay dead because the power is stopped here by this open breaker. Now, you can go down and start a generator up, put it on the board. Once you put it on the board, then this line becomes energized. The system senses that voltage. The next thing that it will do, if it's set in automatic, is it will open the emergency diesel generator disconnect, which means that the emergency bus now goes dead for a few seconds. So as soon as this opens, this goes dead, and anything on that bus, say if you have a cooling water pumps, they're going to shut down, and most likely, because most of our pumps are set up that way, they will not restart. So that's one of the things to be conscious of as you go through this automatic bus transfer process, is that you may have pumps that are operational that will stop during and not restart afterwards, and you have to remember to do that. So anyway, this disconnect breaker will open, the bus goes dead, then your bus tie closes again and re-energizes the emergency off the main switchboard. And this is all done automatically. Now, one thing that isn't automatic, and you have to remember this, is generally on all the systems I've been on, the emergency diesel generator will continue to run. So you do have to remember to go up there and shut it down. So just remember that typically you manually have to shut the emergency diesel generator down afterwards. Now, if you don't want this automatic bus transfer to take place, let's say I'm had a blackout situation and I'm very busy and I don't want to have to restart these equipment on the emergency bus, what I can do is, before I start a diesel generator, open the engine room bus tie. And this is a manual breaker. I can open that up. Then I can power up the main switchboard. It will not energize this line, and the transfer will not take place. And then I can get my work done. And when I'm ready and set up to restart the equipment to do that temporary blackout, all I have to do is close this engine room bus tie, and then that transfer will take place. Some people also test the emergency diesel generator startup by opening this bus tie down in the engine room, and then your generator will start up. Though typically I like to do it using the provided switch, which is on the diesel generator control panel. Now, one of the things that we need to talk about briefly is that these two, the bus tie on the emergency board and the emergency diesel generator disconnect, have an electrical interlock, and it's considered a pretty vital electrical interlock for safety. What this provides for is that those two breakers cannot close at the same time. So when you have the chief put his key in that feedback lever and flip that, what that does is that disconnects this electrical interlock and allows you to close both of these at the same time. There are emergency situations when you've had a blackout and for whatever reason you need to be able to power up the main switchboard to power a piece of equipment that you need. This is allowable, but realize that you have to make sure that you strip the main board prior to doing this, because that emergency diesel generator cannot supply all the loads on the main switchboard. And the other one that you have to realize is that you cannot synchronize the emergency diesel generator with the main generators. The governor system and the automation is not set up typically on the vast majority of American vessels to be synchronized. So the worry is that you would go and start up and forget, and you're on feedback, and start up a diesel generator and put that on the line without synchronizing it. And again, the automation is not set up to synchronize typically. And if your automation on some of the systems, you're doing this manually, it will allow you to do it because it is not looking for that generator. So anyway, whenever you are on feedback, you should lock out, tag out your main generators and not go anywhere near this. If you were to be able to put a main generator on the line with the emergency diesel generator without being properly synchronized, the fault current that is created from that can destroy equipment and destroy the board, and it is absolutely not allowed. So normally the feedback should be locked out. The chief engineer has that key, and he's the only one that's going to authorize the use of this. And then you're only going to use that in an emergency where you have to feed back to the main switchboard to get some piece of equipment. This is not allowed with the Europeans. All right, the next is cold ironing, and this is a new regulation within the state of California. Beginning January 1st, 2014, fleets calling at the California ports must shut down their auxiliary engines and plug into the electrical grid while at berth. There is a single international standard to ensure compatibility among the world's shore power systems. The shore power system will provide power to the vessel using wharf outlets at 6.6 kV, 3-phase, 60 Hz, with a grounding circuit conductor. The design load for each ship is 7,500 kV at kilovolt amps. The shore power outlet will consist of two 350 amp receptacles rated for 6.6 kV, and they are to be housed in a single waterproof enclosure that would be in the dock itself. This is pictures of the electricians down in the Port of Long Beach hooking this up. 6,600 volts is a serious voltage. It has considerable safety considerations that go along with it. If you have not been trained in high voltage systems, you stay away from this. There is a safety factor here. Now, the reason that California is doing this is that the running of auxiliary generators while the vessels are in port are a considerable amount of pollution. By switching over to shore power, they are using cleaner generation systems that meet all the California clean air regulations. So this is becoming more and more required within California. Because this is a normal operation, in the past we used to black out whenever we switched over to shore power. With these systems, you're going to see the vessels set up as this regulations come online and this becomes the norm. And I think it will become the norm in much of North America. Then you will see systems to automatically parallel shoreside and the vessel so that you don't have a disruption of service. All right, this on the simulator is the emergency switchboard. And you have on here, these would be all your feeds to the different equipment. You also have a transformer here. And this is a motorized circuit breaker. For this to operate, by the way, you have to power up this emergency transformer. This circuit breaker, what it does is it sends power to charge the springs in this motorized. And this light comes on, and then you can close that so that you can power up the transformer. The transformer drops 440 volts to 220 volts, which is a European lighting standard. This is your lighting here. This also is the European symbology for a transformer. The other one is you have a battery charger, right, which is also off the board. And then this battery charger sends power to all your battery bank, right? Which is reality is an uninterruptible power supply. And on this is as a standard on most vessels 24 volts. Just as a warning, if you forget to put these on, the simulator is drawing current from these batteries and they will discharge fairly quickly. This main switchboard actually supplies power to your main ship service diesel generators to the voltage regulator, and if that drains, you will not be able to bring up power on the generator. So this would be an example of a battery backup system that you could see on a vessel. And at this point, we'll conclude this section of this lecture. I thank you for your attention, and we'll have fun in class. Thank you very much.